10.2 Lesson 1, Plane Curves and Parametric Equations. Our objectives for today are 1. You'll be able to sketch the curve represented by a set of parametric equations, and objective 2, you'll be able to eliminate the parameter. So we're familiar with rectangular equations. For example, y is equal to 2x plus 1, y is equal to sine x, y is equal to the square root of 1 plus x. These are all rectangular equations where you have y as a function of x, or even x as a function of y. You could even have x as a function of y. But they're rectangular equations. They involve the two variables x and y. And when you graph them, you graph them on the rectangular coordinate plane with an x-axis and a y-axis. Today we're learning about parametric equations. So when you have a set of parametric equations, you have one parametric equation that tells you the x-coordinate of a point, and you have another parametric equation that tells you the y-coordinate of a point. So you have a set of two parametric equations, and you have a third variable in addition to x and y, which are two variables. You have a third variable, and that third variable is called the parameter. Common letters that we use to represent the third variable are t. Sometimes we use theta or some other variable such as s. So those are common letters that we use to represent the third variable called the parameter. We can sometimes consider the parameter to represent time. So you can have, for example, movement of a particle in 2 dimensions as a function of time. And the parametric equations for x and y will tell you the x and the y coordinates of the object's position in the xy plane at a particular time, which is given by the parameter t. You could also have the parameter represent an angle of rotation or even something else, as we will see later. So why do we have parametric equations? Why not just stick with rectangular equations? For one, the parametric equations will give you additional information that we did not have with rectangular equations because of the addition of the third variable called the parameter. For example, if we're talking about an object that's moving in the xy plane, if you just have a rectangular equation, it could tell you the path followed by the object. But if you have a set of parametric equations, in addition to knowing the path followed by the object, we can also know, for example, at what time is the object in a particular location. And there are other things that we can determine, as we will see later as we continue with our study. Because of the additional information given by parametric equations, we make a distinction between graph and curve. So the graph would be just a set of points in the xy plane, and it could represent, for example, the path followed by an object as it is moving in the xy plane. And that would be it. But the curve gives more information. It includes the graph, and it includes the set of parametric equations from which we obtain the graph. And with the set of parametric equations, you'll have additional information about the object's movement, such as the location of the object at a particular time, and if the parameter t represents time. There's also orientation. So if you have a curve, you also know the direction in which the curve is being traced. That is called the orientation, the direction in which the curve is being traced. Sometimes you might just want to easily graph a set of parametric equations. And for that purpose, you may want to represent the graph represented by the set of parametric equations using a rectangular equation. So if you want to go from a set of parametric equations to a rectangular equation, for the purpose of sketching the graph pretty quickly, that process of going from a set of parametric equations to a rectangular equation is called eliminating the parameter. So we went over some vocabulary, and we'd like to start our lesson now by sketching the curve represented by a set of parametric equations, and then we will look at how to eliminate the parameter. So here we have the definition of a plane curve. So if f and g, those are your parametric equations, are continuous functions of the parameter t on an interval I, then the equations f of t, which tells you x coordinates, and g of t, which tell you y coordinates, are called parametric equations. So you have a set of two parametric equations. And t is called the parameter. The set of points x, y obtained as t varies over the interval I is called the graph of the parametric equations. Taken together, the parametric equations and the graph are called a plane curve, denoted by C. And again, the plane curve gives additional information as opposed to just the graph. It would tell you, for example, where the object is at a particular value of the parameter t for time, for example. It could also tell you the direction in which the object is moving. It would also tell you the direction in which the object is moving, which is called the orientation of the curve. So for our first objective, you'll be able to sketch the curve represented by a set of parametric equations. And then for our second objective, we'll be able to eliminate the parameter. We'd like to look at both objectives by using this particular problem. Number one, consider the parametric equations x is equal to the square root of t and y is equal to 1 minus t. Complete the table. So we have some values of the parameter t already filled out in the table. And in this particular case, you could also have t be a negative value. Well, actually, no, I would like to correct myself. In this particular case, you cannot have t be a negative value. Why can't we have t be negative? It's because of the parametric equation for x, which is x is equal to the square root of t. And we know that we cannot take the square root of a negative number using real numbers. So for that reason, the parameter t has to be non-negative. So t is restricted to be either 0 or positive because of the parametric equation for x. So that's why we start the table at t is equal to 0, and then we have some values of t after 0, 1, 2, 3, and 4. And then the parametric equation for y is equal to 1 minus t. Complete the table. Well, it's really easy. So to complete the row for x, you just take the square root of t, because x is equal to the square root of t. So what is the square root of 0? 0. The square root of 1 is 1. The square root of 2 is the square root of 2. You can get a decimal approximation. We'll do that later when we want to graph. The square root of 3 is the square root of 3, and the square root of 4 is 2. And when you want to complete the next row for the parameter, not for the parameter, but for the variable y, we'll go ahead and take a look at that. So for y, we have y is equal to 1 minus the parameter t. So let's just do that and complete the row for y. So we have 1 minus t. When t is 0, 1 minus 0 is 1. When t is 1, 1 minus 1 is 0. When t is 2, 1 minus 2 is negative 1. When t is 3, 1 minus 3 is negative 2. And when t is 4, 1 minus 4 is negative 3. So we know t has to be greater than or equal to 0, as discussed earlier. And we have some ordered pairs corresponding to these 5 values of t from our table. So what do we want to do? we want to sketch the curve represented by this set of parametric equations. So if you look at the instructions, it says complete the table. We've already done that. Part B, plot the points x, y generated in the table and sketch a graph of the parametric equations. Indicate the orientation of the curve. So just by following A, B, C, and D, we'll be achieving the objectives for today's lesson. Objective 1, sketch the curve represented by a set of parametric equations. So we are able to do that now, and we'll go ahead and take a look at that right now. So I'll go ahead and sketch the x and y axes. All right, so we've got 1, 2, 3, 4. 1, 2, 3, 4. So what we do is we just take these ordered pairs and we plot them. So for example, when t is 0, we have the ordered pair 0, 1. So 0, 1 is right here, and that corresponds to t is equal to 0. When t is 1, we have the ordered pair 1, 0, which is right here. That corresponds to t is equal to 1. And when t is 4, we have the ordered pair 2, negative 3. So 2, negative 3 would be about here. And we get that when t is equal to 4. You have two other ordered pairs at t is equal to 2 and t is equal to 3. So you need to figure out what is the square root of 2 approximately. So I'll go ahead and use my calculator. And we have that the square root of 2 is about 1.4. So we have 1.4 for x and negative 1 for y. So you have this point when t is equal to 2. And then when t is equal to 3, you have square root of 3, negative 2. So we need to find the square root of 3, which is about 1.73, and then you have negative 2. So if you look at these points, we can see that we start at t is equal to 0, and now I'm going to trace the curve given by the set of parametric equations. I start at t is equal to 0, the point 0, 1, and then I go to t is equal to 1, to t is equal to 2, to the point given by t is equal to 3, and to the point given by t is equal to 4. And the orientation of my curve is from left to right. You can see that the curve starts here, and it's moving towards the right, and it's going down as well. So that's what we mean by orientation. So this is the graph given by the set of parametric equations, and when we look at the graph together with the set of parametric equations, we have what we call the curve, which gives additional information such as the orientation of the curve, the direction in which the curve is being traced, and also there's other information that we can discuss when we talk about a particle moving in the plane, such as the speed of the particle, where the particle is at a particular time, and so on. So we have indicated the orientation of the curve. I indicated the orientation of the curve by sketching these arrowheads that tell us the direction in which the curve was traced. We will be focusing on using graphing utilities in a later lesson, so we will skip part C for now. If you would like to, you can try to do that. And let's take a look at part D. So part D will help us with our second objective, which is to eliminate the parameter in a set of parametric equations to get a rectangular equation which would give the graph. So find the rectangular equation by eliminating the parameter and sketch its graph. Compare the graph in part B with the graph of the rectangular equation. So that's what we'd like to do. So again, in this problem, this is our set of parametric equations. Sometimes we'll write them like this, just have the parametric equation for x, and underneath it we'll have the parametric equation for y. And sometimes we can indicate that they are a set by using a brace. Or if we don't use the brace, it is understood that they are a set. So find the rectangular equation by eliminating the parameter. So basically, the objective is to combine these two parametric equations into one rectangular equation by eliminating the parameter. And then that would allow us to maybe sketch the graph more easily. So these are the steps for finding the rectangular equation by eliminating the parameter. We start with the given parametric equations. We solve for the parameter in one of the equations. We substitute into the other equation, and that would give us our rectangular equation. So here's step one. We start with our given parametric equations. We'd like to get a rectangular equation. That's our goal. And we'd like to get y as a function of x. So our goal is to have y is equal to some function of x. So with that in mind, we go on to step 2. Solve for the parameter in one equation, and step 3 is to substitute into the other equation. So it would make sense to solve for x in the first parametric equation. Not for x, sorry. Solve for the parameter in the first parametric equation. So it would make sense to solve for the parameter t in the first parametric equation. And once we have t as a function of x, we can then substitute for t in the parametric equation for y, and that would give us a rectangular equation where we have y as a function of x. So it's very easy to solve for t in the first parametric equation. You have x is equal to the square root of t. So if you square both sides of the equation, that would give x squared is equal to t. And once you've done step 2, you know t is equal to x squared. So what you do now is step 3, substitute into the other equation. So we can replace the t in the parametric equation for y with x squared. So our final answer will be y is equal to 1 minus x squared, and that's our rectangular equation. You can see the parameter t has been eliminated. It's no longer a part of the rectangular equation. Now, if you have this rectangular equation by itself, of course, x could be any value if you have the rectangular equation by itself. You can square any number and subtract from 1. And the graph of the rectangular equation would have the other half of the parabola. If you look at the graph of the set of parametric equations, we only have the graph in quadrants 1 and 4, to the right of the y-axis. Why is that? Because when you look at the parametric equation for x, we have x is equal to the square root of t. T has to be greater than or equal to 0, and this is only taking the positive square root. So when you eliminate the parameter, you get this rectangular equation, but you have to indicate that x has to be greater than or equal to 0, so that when you graph this rectangular equation, your graph would match the graph that we got earlier when we were doing part A. So you need to put a restriction on x, so that x has to be greater than or equal to 0. So I rewrote all the steps on the bottom left portion of the screen. So we began with the set of parametric equations. We solved for t in one equation by squaring both sides of the equation. and then we substituted into the other equation, and we got our rectangular equation, y is equal to 1 minus x squared. But considering the restrictions for t for the original set of parametric equations, and considering that we were taking the positive square root of t to get x, we know x has to be greater than or equal to 0, so that when we graph this rectangular equation, it would match the graph that we had earlier obtained by doing part A. When we wrote ordered pairs x, y that corresponded to certain values of t, and plotted those points to get the curve given by the set of parametric equations. So today, we looked at these two objectives. You'll be able to sketch the curve represented by a set of parametric equations, and you'll be able to eliminate the parameter.